Picture this, a vast, swirling tapestry of light and darkness stretching across the endless expanse of space, where every pinprick of brilliance is a galaxy, each with its own epic tale to tell. These celestial cities of stars aren't just static dots in the sky. They're alive, evolving, and hiding stories of cosmic birth, transformation, and even demise. What if you could flip through the pages of their histories like chapters in a grand universal library? That's exactly what we're about to do as we explore the 24 universal chronicles mapping the life cycle of galaxies. A journey that will take us from the fiery dawn of creation to the quiet fade of cosmic twilight. Think about the last time you looked up at the night sky and felt that humbling sense of wonder. Those distant galaxies aren't just pretty lights, they're time capsules, holding clues to how everything we know came to be. Some are newborn, still wrapped in the glowing gas of their stellar nurseries. Others are ancient, their stars burning faintly after billions of years. And then there are the Titans, locked in violent dances with supermassive black holes at their hearts. What ties them all together? A hidden rhythm, a universal life cycle that shapes their destinies just as surely as the seasons shape our world. This isn't just about distant specks of light, it's about our place in the universe. Every galaxy we study is a mirror reflecting back a piece of our own cosmic heritage. By unraveling their stories, we're piecing together the grandest puzzle of all, how stars, planets, and even life itself came to exist. So buckle up. Over the next 24 chronicles, we'll witness galaxies colliding, black holes feasting, and dark matter weaving its invisible web. You'll leave this journey not just with awe, but with something deeper, an understanding that we're all part of this unfolding cosmic epic. Ready to turn the first page? Let's begin. Imagine gravity as the universe's sculptor, patiently gathering scattered clouds of hydrogen and helium, leftovers from the Big Bang's fiery aftermath, and pressing them together until they ignite with the first sparks of starlight. These primordial gas clouds, laced with mysterious dark matter, weren't just floating idly. They were cosmic cradles trembling on the edge of transformation. When densities reached a critical point, something extraordinary happened. Pockets of gas collapsed, temperatures soared, and nuclear fusion lit the fuse for the universe's first stars. Like beacons in the darkness, these early stars didn't just shine, they shaped everything around them. Their fierce radiation carved out cavities in the gas, while their explosive deaths as supernovae seeded space with heavy elements, enriching future generations of stars and planets. Now picture one of these stellar nurseries, not the tidy, isolated image we often see in illustrations, but a frenzied construction site where gravity fights turbulence, and magnetic fields twist gas into spiraling filaments. The ultra-deep field gives us a glimpse of this chaos frozen in time, faint, blobby galaxies glowing like embers in the distant universe. These aren't the grand spirals we know today. They're prototypes, rough drafts written in hydrogen and starlight. Some are small and irregular, destined to merge with others like cosmic puzzle pieces. Others, fed by rivers of gas flowing along dark matter's invisible highways, grow rapidly, their gravity pulling in more material until they become the giants we recognize. But why do some galaxies evolve into elegant spirals with arms swirling like pinwheels, while others become smooth, football-shaped ellipticals? The secret lies in their turbulent youth. A galaxy's rotation speed, the frequency of collisions, even the density of its surroundings, all these factors leave an imprint. Spiral galaxies, for instance, often form in quieter cosmic neighborhoods where gas can settle into orderly disks. Ellipticals, on the other hand, are the products of violent mergers, their stars thrown into chaotic orbits that erase any trace of structure. It's a reminder that galaxies, much like living things, carry the scars and triumphs of their earliest moments. And here's the astonishing part. This process isn't just ancient history. Right now, in some distant corner of the cosmos, a new galaxy is taking its first breath. The ingredients are simple: gravity, gas, and time, but the results are as varied as snowflakes in a storm. Each one begins as a whisper, but given billions of years, that whisper becomes a shout, a story written across the night sky. The universe wasn't always filled with the majestic spirals and glowing clusters we see today. Rewind the cosmic clock more than 13 billion years, and you'd find a realm of darkness barely lit by the first flickers of starlight. These earliest galaxies, like the record-breaking GNZ11, were the pioneers of structure in the cosmos, tiny, turbulent, and impossibly bright for their size. Picture them not as the orderly systems we know, but as frenetic construction sites, where gravity clumped together primordial hydrogen and helium into dense knots that ignited into the universe's first stars. These stars weren't just luminous, they were alchemists, fusing lighter elements into heavier ones like carbon and oxygen in their cores, ingredients that would later become the building blocks of planets and life. What makes these ancient galaxies so extraordinary isn't just their age, it's their hunger. They devoured surrounding gas at a rate modern galaxies can't match, birthing stars in furious bursts that lit up the early cosmos like fireworks. But here's the catch: their light doesn't reach us as the visible glow our eyes perceive. Over billions of years, the expansion of space has stretched their ultraviolet emissions into faint infrared signals, whispers from a time when the universe was less than 5% of its current age. That's why telescopes like James are revolutionary. They're designed to catch these signals, peeling back the layers of time to show us the universe's toddler years. And what do these relics tell us? They're time capsules from an era astronomers call the cosmic dawn, the moment when starlight first began to pierce the fog of the early universe. Before this epoch, space was filled with a murky hydrogen haze, but as galaxies like GNZ11 flickered to life, their radiation ionized the gas around them, clearing the cosmic fog like sunrise burning off morning mist. This transformation, known as, was one of the universe's most pivotal turning points. Without it, light wouldn't travel freely, and the cosmos would remain forever shrouded. But these infant galaxies didn't stay small for long. Gravity, the ultimate architect, drew them together in a slow-motion dance of collisions and mergers. With each union, they grew larger, their chaotic star-forming frenzy settling into more stable rhythms. Some evolved into the elegant spirals we recognize today, while others merged into the colossal elliptical galaxies that dominate galaxy clusters. Yet their legacy lives on. Every atom in our bodies, every planet orbiting distant stars, owes its existence to those first tumultuous generations of galaxies. They didn't just light up the universe, they set the stage for everything that followed. After the cosmic dawn came a fireworks display of staggering proportions. An era when galaxies didn't just form stars but did so with reckless abandon, turning entire regions of space into dazzling stellar factories. This was the stellar boom, a chapter in galactic history where star formation rates skyrocketed to hundreds, even thousands of times what we see in modern galaxies like our Milky Way. Picture the Orion Nebula, that familiar stellar nursery in our own backyard, but across an entire galaxy. Every corner brimming with newborn stars igniting in rapid succession, their collective glow visible across the universe. One of the most dramatic triggers for this frenzy was galactic collisions. When two galaxies locked in a gravitational embrace, their mutual pull sent shockwaves through clouds of gas, compressing them into dense knots ripe for star birth. The Tadpole Galaxy, with its long, star-studded tail stretching across space, is a perfect time capsule from this era. That tail isn't just debris, it's a trail of stellar newborns, yanked outward during a violent encounter with another galaxy millions of years ago. These mergers didn't just reshape galaxies, they supercharged them, turning quiet neighborhoods into cosmic fireworks shows. But collisions weren't the only fuel for this stellar frenzy. Early galaxies swam in vast reservoirs of pristine gas, untouched by previous generations of stars. This gas was the perfect raw material, cool, dense, and abundant. Without heavy elements to act as cosmic coolants, it could collapse rapidly, forming stars at breakneck speeds. Starburst galaxies like Messier 82 still showcase this process today, though on a smaller scale, with their cores churning out stars 10 times faster than our own galaxy. Yet, like all booms, this one couldn't last forever. Two key forces brought the party to a close. First, galaxies simply ran out of fuel. Star formation is a self-limiting process. The more stars you create, the more supernovae erupt, blasting surrounding gas away with their shockwaves. Second, and perhaps more intriguing, was the rise of supermassive black holes. As these monsters grew at the hearts of galaxies, their intense radiation and jets began to heat and disrupt surrounding gas, preventing it from cooling and collapsing into new stars. The very engines that once powered galactic growth eventually became the regulators of their decline. This transition from chaos to order wasn't instantaneous. Some galaxies, like those in dense clusters, exhausted their gas early, leaving behind aging stellar populations. Others, in quieter corners of the universe, continued forming stars at a gentler pace. But one thing was certain: the stellar boom had set the stage for the next great cosmic drama, the era of black hole dominance, where invisible giants would begin to shape galactic destinies in ways no one could have predicted. Hidden in the chaotic cores of nearly every galaxy lies a sleeping giant, a supermassive black hole millions to billions of times heavier than our sun. For eons, these cosmic monsters slumbered, shrouded in darkness. But when a galaxy's gas and stars strayed too close, something extraordinary happened. Like dragons roused from their lairs, these black holes awoke, transforming from silent observers into galactic architects with unimaginable power. Take Sagittarius A star, the Milky Way's own quiet beast. Today it's relatively tame, but evidence suggests it once blazed with the fury of a quasar, its appetite shaping our galaxy's destiny. The awakening wasn't gentle. As matter spiraled into these gravitational pits, friction heated it to millions of degrees, creating swirling disks of plasma brighter than entire galaxies. Some black holes, like the famous quasar 3C273, channeled this energy into jets stretching thousands of light years, cosmic blowtorches carving through interstellar gas. These weren't just spectacular light shows, they were feedback mechanisms on a galactic scale. Radiation and particle winds from the black holes feast heated surrounding gas, preventing it from cooling and collapsing into new stars. In essence, the very engine that could have fueled more star formation instead shut it down. Here, where things get truly fascinating. Astronomers noticed a peculiar pattern. The more massive a galaxy's central bulge of stars, the heftier its black hole. This tight correlation suggests an intricate dance between monster and host, a symbiotic relationship forged over billions of years. Did the black hole regulate the galaxy's growth, or did the galaxy's evolution determine the black hole's size? It's a chicken and egg puzzle that still keeps scientists awake at night. Some theories propose that mergers funneled gas toward galactic centers, feeding both star formation and black holes simultaneously. Others suggest black holes acted as cosmic thermostats, their outbursts preventing galaxies from growing too large. This phase marked galaxies' turbulent adolescence, a time of dramatic growth spurts and growing pains. Quasars flared like cosmic beacons across the young universe, their light visible billions of years later. Galaxy cores shimmered with the glow of heated gas, while black hole jets sculpted vast bubbles in intergalactic space. Yet amid this chaos, balance emerged. The same forces that suppress star formation in a galaxy's inner regions may have redirected gas to its outskirts, fueling growth in new areas. It's a reminder that in the cosmos, destruction and creation are often two sides of the same coin, and that even the most violent processes can lead to astonishing order. Galaxies aren't the solitary islands they appear to be. They're more like celestial predators, locked in an endless cosmic dance of consumption and transformation. Take the antennae galaxies, their long, shimmering tails stretching across space like ribbons of starlight. What we're witnessing there isn't destruction, it's rebirth. As these two spirals entwine, their mutual gravity flings stars outward in dazzling arcs while compressing gas clouds into dense knots where new stars ignite by the millions. This isn't chaos, it's creation wearing a violent disguise. The aftermath of these collisions often defies expectations. Instead of leaving ruins, mergers sculpt something entirely new. When a small spiral galaxy plunges into a larger one, its stars don't simply vanish, they're assimilated, absorbed into the growing halo of their captor. Over billions of years, multiple mergers can transform a delicate spiral like our Milky Way into a behemoth elliptical galaxy like Messier 87, whose smooth, featureless glow betrays its turbulent past. These galactic giants dominate galaxy clusters not because they formed that way, but because they've spent eons consuming their neighbors. But here's what's truly remarkable. Galaxies don't just passively collide, they communicate. Their dark matter halos, those invisible cocoons that outweigh all their visible stars, act as cosmic negotiators. As two galaxies approach, their dark matter halos intermingle first, absorbing the brunt of the impact like shock absorbers. This invisible scaffolding determines whether the encounter will be a glancing blow or a full merger, whether stars will be scattered like dust or woven into a new structure. Without dark matter's guiding hand, galaxies would tear themselves apart, their stars lost to the void. The creative destruction doesn't stop with stars. Galactic mergers awaken sleeping monsters, supermassive black holes that may have lain dormant for billions of years. As fresh gas floods into galactic centers during collisions, these black holes feast, transforming into blazing quasars that outshine entire galaxies. Even after the quasars fade, the black holes remain, eventually pairing up in gravitational duels that send ripples through spacetime itself. We've detected these ripples, gravitational waves, from black hole mergers over 1 billion light-years away, echoes of ancient galactic battles. Yet for all their violence, these collisions follow an elegant rhythm. Computer simulations reveal how streams of stars pulled from merging galaxies form intricate bridges and shells, patterns we can now spot in nearby galaxies like NGC 4745. These stellar fossils tell us mergers aren't rare catastrophes, they're the universe's preferred method of growth. Our own Milky Way bears the scars of past encounters, and in about 4 billion years, will collide with the Andromeda galaxy. Far from doomsday, this will be a new beginning, a fiery spectacle that will reshape our cosmic neighborhood into something unrecognizable yet breathtaking. What looks like cannibalism is really the universe's way of reinventing itself. Every time galaxies merge, they recycle their materials into new stars, new planets, and perhaps, on worlds we'll never see, new possibilities for life. The antennae galaxies aren't dying, they're giving birth to the next chapter of cosmic history, proving that in the grand story of galaxies, endings and beginnings are often the same thing. Picture a sculptor shaping clay with hands you can't see. That's dark matter's role in the cosmic workshop. Though invisible, this mysterious substance outshines ordinary matter 5-1, weaving an unseen scaffold that holds galaxies together. Without its gravitational embrace, stars at the edges of spiral galaxies like our Milky Way would fling into the void, their speeds too great for visible matter alone to contain. The proof isn't just in theory, it's etched across the sky. Take the Bullet Cluster, where two galaxy clusters collided in one of the most violent cosmic events ever observed. X-ray telescopes revealed a shockwave of hot gas lagging behind, while gravitational lensing maps showed the bulk of mass, the dark matter, had sailed ahead, parting ways with the visible material like an invisible ghost walking through walls. What makes dark matter so baffling isn't just its invisibility, it's how stubbornly it resists detection. Unlike black holes, which announce their presence by bending light and swallowing stars, dark matter neither emits nor absorbs radiation. It doesn't clump into planets or stars. Instead, it forms vast, diffuse halos that stretch 10 times farther than a galaxy's visible edge. These halos act as cosmic anchors, their gravity dictating how galaxies rotate, merge, and even how they're born. Simulations of the early universe show dark matter's gravitational wells were the nurseries where gas first pooled, igniting the fires of the earliest stars. Without it, galaxies as we know them simply wouldn't exist. Yet for all its influence, dark matter remains a riddle wrapped in an enigma. Is it a yet undiscovered particle, like the hypothetical WIMPs, weakly interacting massive particles, that physicists have hunted for decades in underground labs? Or could it be something stranger, like primordial black holes formed in the universe's first chaotic moments? The answer might lie in the outliers, galaxies that defy the rules. Consider Dragonfly 44, a dim, diffuse galaxy in the Coma cluster. It emits barely 1% of the Milky Way's light, yet its stars move at speeds betraying a dark matter halo thousands of times more massive than expected. Then there's NGC 1052, a galaxy with almost no dark matter at all, challenging the assumption that it's indispensable. These oddballs force us to rethink dark matter's story. Perhaps it interacts with itself in ways we haven't imagined, or maybe gravity itself behaves differently on cosmic scales. The search for answers has spawned ingenious experiments, from detectors buried deep in mines to telescopes mapping the cosmic microwave background for shadows of dark matter's fingerprints. Every galaxy we study, every collision we observe, adds another piece to the puzzle. One thing's certain, dark matter isn't just a passive backdrop. It's the universe's silent architect, shaping the visible cosmos with hands we're only beginning to sense. And as we peer deeper into the dark, we might find that the outliers, the exceptions, hold the keys to the greatest cosmic secret of all. Some galaxies refuse to follow the cosmic rulebook, flaunting shapes and behaviors that defy every textbook diagram. Takes object, a perfect ring of blue stars encircling a golden core like a celestial bull's floating in space. It's not the aftermath of a collision or a trick of perspective. This cosmic oddball has maintained its pristine symmetry for billions of years, a mystery that challenges our ideas of galactic evolution. Then there's NGC 1277, a compact relic galaxy that time forgot. Packed with ancient stars and barely any new ones, it's a fossil from the universe's fiery youth, preserved against all odds in the modern cosmos. These outliers aren't just curiosities, they're cosmic experiments, natural laboratories testing the limits of physics. Ultra-diffuse galaxies like Dragonfly 44 stretch this boundary further. They're as wide as the Milky Way but contain just 1% of its stars, their dim glow barely visible against the blackness of space. How do such fragile structures survive the turbulence of galaxy clusters? The answer might lie in dark matter. Their invisible halos could be denser than expected, acting like cosmic shock absorbers. On the opposite extreme are quasars, the universe's ultimate overachievers. These brilliant cores of distant galaxies outshine every star around them, powered by supermassive black holes feasting on unimaginable amounts of gas. But even here, there are rebels. Some quasars flicker on and off like cosmic light switches, their erratic behavior suggesting black holes might choke on their meals, temporarily shutting down their own energy production. What unites these misfits isn't just their strangeness. It's what they reveal about the universe's flexibility. Galactic collisions can stretch a spiral into a ring, tidal forces can rip stars into ghostly streams, and sheer luck can preserve ancient relics in a cosmos that favors change. Each oddball galaxy is a reminder that the universe writes its rules in pencil, not ink. And as we'll soon see, even the most stable galaxies aren't immune to the inevitable. The slow march toward their twilight years. Every story has its twilight, and galaxies are no exception. Imagine a once bustling metropolis where the factories have gone quiet, the streets emptied, only the faint glow of aging streetlights remains. That's the fate of galaxies like those in the Coma cluster, cosmic relics now labeled red and dead. Their vibrant blue star-forming regions have vanished, leaving behind a population of elderly red stars quietly burning through their final fuel. But this isn't just a tale of passive fading. It's a slow-motion drama shaped by three cosmic villains: exhaustion, interference, and theft. First, the exhaustion. Star formation is a self-limiting process. It's like building a fire with the same pile of logs. Early galaxies burned through their pristine hydrogen gas with abandon, but each generation of stars locked away more of that fuel in stellar cores or blew it back into space as supernova debris. Over time, the available gas became laced with heavier elements, making it harder to collapse into new stars. The Milky Way's current star formation rate is just a trickle compared to its heyday, a mere 3 suns per year. But in galaxy clusters like Coma, the situation is more dire. There, galaxies orbit through hot, thin intergalactic gas that's too diffuse to cool and replenish their dwindling reserves. Then comes the interference. Remember those supermassive black holes we met earlier? Their role isn't over when quasars fade. Even in their quieter phases, these monsters periodically belch out jets and radiation, heating surrounding gas like a cosmic, blowing away a pile of leaves. This feedback prevents gas from cooling and collapsing into new stars, effectively putting a lid on galactic rebirth. In massive elliptical galaxies, this process has reached its conclusion. Their gas is too hot, too stirred up to ever form stars again. But perhaps the most dramatic thief is the environment itself. Galaxy clusters are gravitational whirlpools, and as member galaxies plunge through them, they face a brutal process called ram pressure stripping. Picture a comet's tail, but instead of ice vaporizing in sunlight, it's an entire galaxy's gas reservoir being torn away by the pressure of moving through material. The iconic Sombrero Galaxy shows signs of this. Its once-rich gas disk now appears shredded, leaving behind a stark silhouette of dust against a backdrop of aging stars. Yet even in decline, there's poetry. The Milky Way's twilight won't be a simple fade to black. Simulations suggest that as our galaxy's remaining gas reservoirs destabilize in its final epochs, they'll trigger one last stellar baby boom, a frosting of newborn stars against a canvas of red giants. This brief resurgence won't last. Without fresh gas inflows, star formation will sputter out entirely in about 5 billion years. But for a fleeting moment, our galaxy will wear a crown of young blue stars, a final salute to its glory days before joining the silent majority in the cosmic graveyard. What's astonishing is how much of this fate hinges on recycling. The same heavy elements forged in ancient stars, carbon, oxygen, iron, become the seeds for future star formation when expelled in supernovae or stellar winds. In galaxies like Andromeda, we see this cycle in action. Vast reservoirs of enriched gas waiting to be stirred up by collisions or spiral arm disturbances. It's a reminder that even in fading, galaxies obey the universe's great law: nothing is truly lost, only transformed. The stars that blaze briefly in a galaxy's final act are made from ashes of the first. Death is never the end in the cosmic scheme. It's the universe's most efficient recycling program. When a star like our sun reaches its final act, it doesn't simply vanish. Instead, it sheds its outer layers in a slow, luminous exhale, creating a planetary nebula, one of space's most breathtaking performances. The Helix Nebula, with its eerie blue eyes staring across 1,300 light-years, isn't just a farewell, it's a delivery system. That glowing gas contains carbon, nitrogen, and oxygen forged in the star's core, elements destined to become the building blocks of future planets and perhaps even life. But the real spectacle comes with the giants. Massive stars don't fade quietly. They go out in supernova explosions so powerful they briefly outshine entire galaxies. The Crab Nebula is a prime example, a tangled web of gas and magnetic fields where a star detonated in 1054. That cataclysm didn't just scatter stardust. It forged heavier elements like gold and uranium, seeding the cosmos with materials no ordinary star could produce. These explosions are the ultimate cosmic alchemists, transforming simple hydrogen into the periodic table's full richness. Here's where the recycling magic happens. Supernova shockwaves plow through interstellar clouds, compressing them until gravity takes over and new stars ignite. The Orion Nebula showcases this process in action. Its glowing gas is laced with elements from dead stars, now fueling a fresh generation of suns. Every young star there owes its existence to ancestors that perished ago. Even our solar system carries this legacy. The iron in your blood and the calcium in your bones were forged in stellar furnaces that died before Earth formed. Yet this cycle isn't infinite. In galaxy clusters like Virgo, the rules change. Their galaxies race through space at millions of kilometers per hour, and the thin, superheated gas between them acts like a cosmic sandblaster. As galaxies move, this intergalactic medium strips away their gas reserves, a process called ram pressure stripping. The result, galaxies like Messier 86, which trails a ghostly tail of lost gas stretching for hundreds of thousands of light years. Without fresh material, these galaxies can't form new stars, dooming them to a slow fade into red-and-dead obsolescence. But nature always has exceptions. Spiral galaxies like NGC 408 defy the odds, thriving in hostile cluster environments. Their secret, a combination of sturdy gas reservoirs and fortuitous orbits that minimize stripping. Others, like the jellyfish galaxy JO201, turn loss into opportunity. Their stripped gas forms bright tendrils where new stars ignite, creating dazzling trails of rebirth even as their main bodies are dismantled. These survivors prove that while the universe favors entropy, it always leaves room for pockets of defiance, islands of renewal in a sea of fading embers. The most astonishing twist might be what happens when recycling finally stops. In galaxies that exhaust their gas, the last generation of stars burns quietly for trillions of years, their light gradually dimming as they consume the final ashes of their ancestors. Yet even this isn't truly the end, just a pause. Given enough time, chance encounters between brown dwarfs and dead stars could spark new flares of nuclear fusion, creating temporary zombie stars in a universe thought to be cold and dark. The cycle continues, just on timescales beyond human imagination. In the cosmic equivalent of a quiet countryside far from bustling cities, galaxies like NGC 1600 exist in peaceful isolation, untouched by the violent mergers and gas-stripping forces that shape their clustered cousins. These cosmic hermits are the universe's late bloomers, galaxies that took the scenic route to maturity, conserving their gas reservoirs like careful savers, while others spent theirs in frenzied starbursts billions of years ago. While most galaxies in crowded clusters have long since faded into red and dead retirement, these outliers continue forming new stars at a leisurely pace, their spiral arms still aglow with youthful blue clusters. What makes these loners so special isn't just their longevity, it's the clues they hold about alternative paths of galactic evolution. Take NGC 2992, a spiral galaxy floating in a near-empty region of space. Unlike the Milky Way, which has endured multiple collisions, this galaxy's pristine structure suggests it's lived a life of remarkable solitude. Its gas remains untainted by the heavy elements abundant in cluster galaxies, offering astronomers a glimpse of what star formation might have looked like in the early universe: pure, uncomplicated, and slow. But solitude comes with its own quirks. Without the gravitational jostling of neighbors, these galaxies often sport unusually large reservoirs of cold hydrogen gas, the raw material for star birth, pooled in their outskirts like untouched reserves. Some, like the faint Leo T-Dwarf galaxy, even harbor gas clouds so delicate they'd have been torn apart in busier cosmic neighborhoods. Yet this isolation isn't perfect protection. Over time, these galaxies face a subtler threat: the universe's expansion. As space stretches, the tenuous filaments of gas connecting them to the cosmic web grow thinner, eventually cutting off their supply lines. Star formation doesn't end with a bang here, but with a slow, inevitable whisper. Even so, these late bloomers have surprises left. Some, like UGC 3672, defy expectations by hosting supermassive black holes far larger than their modest stellar populations should allow. Others, like the ultra-diffuse galaxy Dragonfly 44, challenge our understanding of dark matter's role, with mass distributions that don't fit the usual models. Each outlier is a reminder that the universe has more than one recipe for galaxy formation, and that the quietest corners of space might hold the loudest lessons. The final fate of these stragglers is no less dramatic than their clustered counterparts, just delayed. As the universe expands and cools, even their shielded gas will eventually dissipate or heat beyond usefulness. The last stars will flicker out, leaving behind skeletons of dead stars and black holes. But for now, they glow as cosmic time capsules, proving that in the grand story of galaxies, there's no single right way to live, only countless paths through an ever-changing cosmos. The universe isn't just expanding, it's accelerating, as if some unseen hand has pressed down on the cosmic gas pedal with terrifying force. This mysterious driver is dark energy, an enigmatic force that makes up nearly 70% of the universe's content and behaves unlike anything we've encountered. While gravity tries to pull galaxies together, dark energy pushes space itself apart, stretching the fabric of existence faster and faster with each passing eon. The consequences are both profound and unsettling. Billions of years from now, galaxies beyond our local group, the Milky Way, Andromeda, and their smaller companions, will be racing away so quickly that their light can no longer reach us. They'll vanish beyond what astronomers call the cosmic horizon, not because they've moved, but because the space between us is growing faster than light can traverse it. It's as if the universe is building invisible walls, sealing galaxies into isolated pockets of darkness. Picture this future, a sky stripped of its grandeur. The constellations we know today will have long since scattered, and the distant glow of galaxy clusters like Virgo or Coma will fade into oblivion. Even the cosmic microwave background, the afterglow of the Big Bang, will into undetectable radio waves. The only visible objects will be those bound to us by gravity's unbreakable grip, the merged remains of the Milky Way and Andromeda, now a single, colossal elliptical galaxy some call. This will be the last island in an ocean of nothingness, its aging stars providing the only illumination in an otherwise lightless cosmos. Yet before this lonely fate unfolds, galaxies have one final dramatic act to perform. As star formation sputters out and gas supplies dwindle, the supermassive black holes at their centers will become the dominant players. With no fresh material to feed on, these monsters will turn to the only remaining fuel source, the stars themselves. Over trillions of years, gravitational interactions will fling some stars into the void while nudging others into deadly orbits around the black hole. One by one, they'll be torn apart in tidal disruption events, brief flares of light in an otherwise darkening universe. The largest black holes, now weighing in at hundreds of billions of solar masses, will emit faint Hawking radiation as they slowly evaporate, their final whispers lasting longer than the current age of the cosmos. But here, the haunting twist. Even this bleak future isn't truly the end. Quantum fluctuations in the vacuum of space could, given enough time, spawn new particles, new energies, perhaps even new universes in a cycle beyond our comprehension. The same dark energy accelerating the universe's expansion might one day decay, triggering a new Big Bang in a distant epoch. The story of Galaxies, then, isn't a tragedy, but a single chapter in a saga far grander than we can yet imagine. For now, we're privileged witnesses to a vibrant, evolving cosmos, one where light still travels freely, and the night sky remains a tapestry of countless stories waiting to be told. Imagine a universe where all the stars have burned out, their ashes scattered across light years of darkness. The only structures left standing in this cosmic graveyard are black holes, silent, patient, and impossibly dense. These aren't the vibrant, feeding monsters of earlier epochs. They're the last sentinels of a bygone era, slowly leaking their essence into the void through a process as strange as it is inevitable: Hawking radiation. The idea that black holes could evaporate at all was revolutionary when Stephen Hawking proposed it in the 1970s. According to quantum theory, empty space isn't truly empty. It crackles with virtual particles popping in and out of existence. Normally, these particle pairs annihilate each other instantly. But at a black hole's event horizon, something extraordinary happens. One particle falls in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over incomprehensible stretches of time, this slow leak causes the black hole to lose mass, shrinking until, in theory, it vanishes in a final burst of radiation. Here, where the timeline becomes mind-bending. A black hole with the mass of our Sun would take around 10 to the 67th years to evaporate, a number so vast it dwarfs the current age of the universe by 57 orders of magnitude. The supermassive black holes anchoring galaxies. Those could linger for 10 to the 100th years or longer, yet even these titans aren't eternal. As the eons pass, the universe will grow colder and darker, the black holes themselves becoming the only sources of warmth in an otherwise frigid cosmos. But this isn't just a story of endings, it's a puzzle with tantalizing loose threads. Some theories suggest that when a black hole nears its final moments, quantum gravitational effects might become dominant, warping spacetime in ways we can't yet predict. Could the dying gasp of a black hole birth a new universe, its singularity rebounding in a new Big Bang? It's a speculative idea, but one that fits into larger theories about cyclic cosmologies, where universes are born from the remnants of their predecessors. The black hole era forces us to confront the ultimate fate of information in the cosmos. According to quantum mechanics, information can't be destroyed, yet black holes seem to erase it when matter crosses their event horizons. Hawking's original calculations suggested this information was lost forever, sparking a decades-long debate known as the black hole information paradox. Recent breakthroughs in string theory and holography hint at resolutions, proposing that information might be encoded on a black hole's surface or radiated back out during evaporation. If true, even in the universe's final act, nothing is truly forgotten, just transformed beyond recognition. Long after the last stars flicker out and galaxies dissolve into darkness, black holes will continue their slow fade, their radiation the only testament to a once vibrant cosmos. Yet in their quiet demise, they might hold the seeds of something new, a whisper of rebirth in the endless dark. The universe's story doesn't end with them, it merely turns a page we can't yet read. Hidden in the faint glow of ancient stars lies the universe's oldest archive, a library not of parchment and ink, but of chemical elements and orbital paths. Galactic archaeologists don't need shovels or brushes, their tools are spectrographs and supercomputers, teasing out stories from the slightest shifts in starlight. Take Segue 1, a dim dwarf galaxy orbiting the Milky Way. At first glance, it's unremarkable, just a smudge of old stars. But peer closer, and its chemistry betrays a dramatic past. The iron-to-hydrogen ratio in Segue-1 stars is thousands of times lower than our Sun's, a telltale sign that these stars formed before supernovae had seeded the cosmos with heavy elements. They're living fossils, preserving the pristine conditions of the early universe like time capsules suspended in space. The real breakthrough comes when we study not just what these stars contain, but how they move. Stars in galaxies don't orbit randomly. Their paths are like ribbons trailing through time, recording every galactic merger, every close encounter. The Milky Way's halo is crisscrossed with stellar streams, ghostly rivers of stars torn from dwarf galaxies eons ago. One of the most famous, the Gaia Sausage Stream, is the debris of a colossal collision 9 to 10 billion years ago, when a galaxy 1/5 the Milky Way's size plunged into our own. The stars from that cataclysm didn't assimilate peacefully. Their elongated, plunging orbits are cosmic fingerprints, revealing the violence of that ancient merger. But galactic archaeology isn't just about collisions, it's about resurrection. Some of the oldest stars in our galaxy, like the red giant SMSS J030 4.78-60-852.3, thankfully nicknamed Nasty Star by astronomers, carry traces of elements forged in the universe's very first supernovae. These weren't the orderly explosions we see today. They were hyperenergetic events from stars 200 times the Sun's mass, their death seeding space with bizarre element ratios modern supernovae can't replicate. Finding a star like Nasty Star is like stumbling upon a cave painting from the dawn of time, a direct window into an era when the rules of stellar life and death were still being written. The most astonishing revelations come from pairing chemistry with motion. The galaxy Hercules, another Milky Way satellite, has stars with wildly different metal contents, yet nearly identical orbits. This cosmic contradiction suggests Hercules isn't a pristine dwarf galaxy at all. It's the mangled remnant of a much larger galaxy that was shredded by tidal forces, leaving only its metal poor core behind. Meanwhile, stars in the Milky Way's thick disk, a pancake-shaped population older than our familiar spiral arms, rotate slightly out of sync with the rest of the galaxy, a relic of a time when the young Milky Way was a turbulent, chaotic place. Black holes, too, leave archaeological traces. The supermassive black hole at our galaxy's center, Sagittarius A star, is surrounded by a cluster of stars orbiting at breakneck speeds. Their tight, chaotic paths suggest they formed far away and were dragged inward during a violent merger, carrying with them clues about the black hole's growth spurt billions of years ago. Even stranger are stars, lonely suns flung outward so fast they're escaping the galaxy entirely. These intergalactic fugitives were likely launched by gravitational slingshots during past black hole encounters, their speeds a permanent record of long-ago chaos. What emerges from this detective work is a revelation. Galaxies aren't just objects, they're palimpsests, their histories written over and over in stellar motions and elemental abundances. Every star is a witness, every chemical ratio a clue. As telescopes like James and upcoming missions like the Nancy Grace Roman Space Telescope peer deeper into this cosmic archive, we're not just learning about galaxies' pasts, we're uncovering the origin story of everything, from the atoms in our bodies to the black holes lurking in the dark. The universe forgets nothing, we just had to learn how to read its memory. The Milky Way isn't just our galactic address. It's a living scrapbook of cosmic history, its pages written in starlight and traced by gravity. Thanks to missions like Gaia, which has mapped the positions and motions of over 1 billion stars, we're piecing together our galaxy's dramatic autobiography. One of the most startling revelations. The Milky Way is a cannibal, its graceful spiral arms built from the remains of smaller galaxies it devoured long ago. The evidence is etched in the paths of ancient stars whirling through our galactic halo, their orbits telling tales of violent mergers billions of years in the past. Take Gaia Enceladus, the ghost of a dwarf galaxy that collided with the Milky Way around 10 billion years ago. When Gaia's data revealed groups of stars moving in unexpected retrograde orbits, astronomers realized they were looking at cosmic debris, the last survivors of a galactic feast. This collision didn't just add stars, it reshaped our galaxy's very structure, triggering bursts of star formation that may have contributed to the thick disk of older stars we see today. The merger was so violent that it scattered stars far above and below the galactic plane, creating the diffuse halo that now surrounds us like a celestial fog. But the Milky Way's appetite isn't confined to the distant past. Right now, 25,000 light-years away, the Sagittarius dwarf spheroidal galaxy is being torn apart in slow motion. This tiny satellite galaxy has orbited our own for billions of years, each pass stripping away more of its stars in shimmering streams that wrap around the Milky Way like ribbons. Gaia's precise measurements show these stellar rivers, one leading, one trailing, arching through intergalactic space, their shapes revealing secrets about our galaxy's invisible dark matter halo. The Sagittarius streams aren't just casualties, they're delivery systems bringing fresh stars and perhaps even gas to fuel future star birth. Beyond these dramatic encounters, subtler clues abound. The Milky Way's spiral arms, once thought to be static structures, are now understood as dynamic density waves, cosmic traffic jams where gas compresses and new stars ignite. By tracking the motions of young, hot stars, astronomers have found that our solar system moves in and out of these arms over time, like a car passing through alternating stretches of city and countryside. Even our galaxy's central bar, a thick structure of stars cutting across the core, plays a role in this dance, rotating independently of the spiral arms and funneling gas toward the supermassive black hole at our center. Perhaps the most surprising discovery is that the Milky Way isn't flat. Detailed measurements of Cepheid variable stars, cosmic lighthouses whose pulsations reveal their distances, show our galaxy warping at the edges, its disk bending upward on one side and downward on the other like a record left too long in the sun. This twist, likely caused by past interactions with satellite galaxies or intergalactic gas clouds, proves that even mature galaxies like ours remain works in progress. Every new data set adds depth to this story. The oldest stars in the Milky Way's bulge, some over 13 billion years old, whisper of a time before the spiral arms formed. Chemical fingerprints in their light reveal they were born in frenzied bursts of star formation, their composition strikingly different from younger stars like our Sun. Meanwhile, stars racing through intergalactic space bear witness to past close encounters with Sagittarius A star, our central black hole. Their speed's a permanent record of gravitational slingshots that occurred long before humans looked skyward. What emerges isn't just a portrait of our galaxy, but a revelation about how all galaxies grow, not in isolation, but through a complex web of collisions, mergers, and steady accretion. The Milky Way's history is still being written, its next chapters waiting in the form of future mergers with the Large Cloud and eventually Andromeda. For now, we're privileged to live in a dynamic, ever-changing galactic home, one whose past is only beginning to come into focus. Right now, Andromeda is racing toward us at 110 kilometers per second, a cosmic bullet with our name on it. But don't panic just yet. We've got 4 billion years before the collision begins. When it does, this won't be some chaotic demolition derby. Galaxies are mostly empty space, so the stars themselves will glide past one another like ghosts, their chances of direct impact vanishingly small. What will change is everything about their orbits, as the mutual gravity of these two titans tangles their structures beyond recognition. Picture the first encounter. Andromeda's disk, currently a perfect spiral, will warp and distort as tidal forces stretch it into grotesque shapes. The same gravitational tug will yank the Milky Way's spiral arms out of alignment, flinging stars into long, looping trajectories. Some will be catapulted into the galactic halo, while others will plunge toward the crowded core. All this chaos has an upside. As gas clouds collide and compress, they'll ignite a fireworks show of star formation. Regions that haven't seen stellar birth in billions of years will suddenly blaze with newborn blue giants, their light painting temporary masterpieces across the merging galaxies. Over the next billion years, the real transformation unfolds. After their first close pass, the Milky Way and Andromeda will separate slightly, only to fall back together in a slower, more destructive embrace. This time, their central black holes, Sagittarius A star and its Andromeda counterpart, will begin a gravitational dance, circling each other in ever-tightening orbits. The energy they shed in this cosmic waltz will fling even more stars into chaotic paths, erasing any trace of the original spiral structures. What emerges won't resemble either galaxy. It'll be a messy, glowing blob, an elliptical galaxy in the making. The final act belongs to the black holes. After spiraling inward for millions of years, they'll merge in a spectacular outburst of gravitational waves, sending ripples through spacetime itself. The recoil from this collision might kick the newly formed supermassive black hole into an off-center orbit, a lopsided heart beating inside the galaxy it helped create. By then, the starburst frenzy will have faded, leaving behind a population of aging stars and the faint glow of stellar remnants. This is a redder, quieter, but far larger galaxy than either of its progenitors. Yet even this isn't the end of the story. The merger will send shockwaves through our local group, potentially disrupting nearby galaxies like the Triangulum. Some simulations suggest the combined gravity of might eventually pull in other dwarfs, creating a true galactic empire. And here's the twist. By the time this future unfolds, the accelerating expansion of the universe will have carried all other galaxies beyond our visible horizon. We'll stand alone, the last island in an ocean of darkness, its stars bearing silent witness to a cosmic past we're only beginning to understand. Galactic clusters are the universe's grandest metropolises, sprawling cities where thousands of galaxies gather, drawn together by gravity's invisible hand. The Virgo cluster, our nearest such neighbor, is a perfect example. Over 1,300 galaxies call it home, each one orbiting a common center like bees swarming around a hive. But this isn't some serene cosmic dance. It's a high-stakes survival game where galaxies are shaped, stripped, and sometimes even destroyed by their environment. At the heart of every cluster lies its heaviest player, a supermassive galaxy, often an elliptical monster like Messier 87 in Virgo. These giants didn't grow by chance. They're the product of countless mergers, their gravity pulling in smaller galaxies like cosmic magnets. Surrounding them is a sea of hot gas, heated to millions of degrees by the sheer energy of galaxies plunging through it at thousands of kilometers per second. This gas glows brightly in X-rays, painting clusters as some of the most energetic places in the universe. But that same gas is also a galactic thief. As smaller galaxies orbit through the cluster, they face a brutal process called ram pressure stripping. Picture a car driving through a heavy rainstorm. The raindrops hitting the windshield are like the cluster's hot gas, and the windshield wipers struggling to keep up are the galaxy's own gas reserves being torn away. The result, star-forming material is stripped, leaving behind a galaxy that can no longer birth new stars. Over time, these galaxies fade into the red and dead population, their blue spiral arms replaced by the dull glow of aging red stars. Gravity doesn't just reshape galaxies here, it warps the very fabric of space. The combined mass of a cluster bends light from more distant objects, creating eerie optical illusions called rings. These perfect circles of distorted light are nature's magnifying glasses, allowing us to peer at galaxies far beyond the cluster itself. The bullet cluster takes this phenomenon further. It's actually two clusters colliding, with the visible galaxies lagging behind the bulk of their mass, which is carried by dark matter. This cosmic traffic accident provides some of the clearest evidence we have for dark matter's existence. Our local group, by comparison, is a quiet village. The Milky Way, Andromeda, and their satellite galaxies drift in relative isolation, shielded from the violent stripping and collisions that dominate denser regions. That solitude comes with perks. Our gas-rich spirals can continue forming stars for billions of years, unlike their cluster-dwelling cousins. But even we aren't entirely safe. As the universe expands, gravity's pull will eventually draw us toward the Virgo cluster's outskirts, though by then, the cosmos may be too old for star formation to matter. Galactic clusters are more than just collections of galaxies. They're cosmic laboratories where the most extreme physics plays out. From the superheated plasma between galaxies to the dark matter weaving its unseen web, these structures hold the keys to understanding how the universe organizes itself on the grandest scales. And for galaxies caught in their grip, the choice is simple: adapt or fade away. The universe isn't just a scattering of galaxies, it's a tapestry, woven with threads of dark matter stretching billions of light years in an intricate pattern astronomers call the cosmic web. Picture it like a sponge. Vast filaments of galaxies strung along invisible highways, intersecting at dense nodes where clusters collide, while enormous voids, regions nearly empty of matter, yawn between them. Our own Milky Way doesn't float in isolation. It's part of something far grander, the supercluster, a sprawling gravitational empire 500 million light-years wide, containing 100,000 galaxies all moving together toward a mysterious point in space known as the Great Attractor. This cosmic architecture didn't form by accident. Its blueprints were drawn in the universe's first trillionth of a second, when quantum fluctuations, tiny, random variations in energy, imprinted themselves on the fabric of spacetime. As the universe expanded, these microscopic wrinkles grew under gravity's pull, amplifying into the denser regions where galaxies would later form. The dark matter, invisible and pervasive, acted as scaffolding, its gravity drawing ordinary matter into the filaments and nodes we see today. It's a staggering thought. The distribution of galaxies across the night sky traces back to subatomic tremors from the dawn of time. Superclusters aren't just clusters of galaxies, they're rivers of motion, with entire galaxies flowing along gravitational currents. Imagine standing by a river watching leaves drift downstream. Galaxies behave similarly, their paths revealing the pull of denser regions hidden behind cosmic horizons. The Great Attractor, a gravitational anomaly in its core, tugs not just on the Milky Way but on every galaxy in our local volume, a reminder that even on these scales, gravity's reach is irresistible. Yet the attractor itself is just a waypoint, along with neighboring superclusters, is part of an even larger flow toward the supercluster, the most massive concentration of matter in our observable universe. The cosmic web isn't static. Simulations like the Millennium Run show it evolving over billions of years, filaments tightening as galaxies slide along them, drawn into clusters where they'll eventually merge. Some regions grow emptier as expansion stretches the voids wider, while others condense into knots of unimaginable density. Even now, new filaments are forming at the edges of the observable universe, their light too faint for current telescopes to detect. But missions like the Euclid Space Telescope aim to map this hidden geography by tracing the distortion of distant galaxies, light, a technique called weak gravitational lensing, revealing the dark matter skeleton beneath. What's most humbling is how this structure mirrors nature on every scale. Neurons in the human brain, capillary networks in leaves, even the distribution of galaxies in a supercluster, all share similar branching patterns, as if the universe has a favorite way to organize complexity. Whether this is mere coincidence or a deeper law remains unknown, but one thing is clear. The cosmic web connects everything, from the quantum ripples of the early universe to the galaxies we see today. And somewhere in its vast design, on an unremarkable filament in an ordinary supercluster, our Milky Way spins quietly, a single thread in the grandest tapestry of all. Don't let their size fool you. Dwarf galaxies are the unsung heroes of the cosmos, packing more secrets into their small frames than some giants 1,000 times their size. Take the Large Cloud, our Milky Way's most prominent satellite. Though it's just 1/10 the mass of our galaxy, it's a powerhouse of star formation, its gas-rich clouds birthing new stars at a rate that puts our quieter galactic neighborhood to shame. But what makes these diminutive galaxies truly remarkable isn't just what they're creating, it's what they've preserved. While larger galaxies like ours have cycled their gas through generations of stars, enriching it with heavy elements, many dwarfs harbor pockets of pristine hydrogen and helium, virtually unchanged since the dawn of time. These cosmic time capsules offer a direct window into the conditions of the early universe, before supernovae peppered space with metals. Then there are the ultra-faint dwarfs like Segway 1, so dim they were discovered only in the last 2 decades, lurking in the Milky Way's shadow. Segway 1's starlight is so feeble you could miss it against the glow of a single, yet its gravitational pull tells a different story. The motions of its stars reveal a shocking truth. This galaxy is 99% dark matter, a ratio unmatched by any known structure. For physicists, these dark matter-dominated dwarfs are like celestial laboratories, their simplicity making them ideal for testing theories about how this mysterious substance behaves. Unlike sprawling spirals where gas, stars, and black holes complicate the picture, Segway 1's stark composition lets scientists isolate dark matter's gravitational signature with unprecedented clarity. But the surprises don't stop there. Some dwarf galaxies, like Triangulum 2, host stars with bizarrely low metal content, so low they shouldn't exist under standard models of cosmic chemical evolution. These stars likely formed from gas polluted by just 1 or 2 supernovae, their chemical fingerprints preserving the unique yields of the universe's very first stellar explosions. Others, like the recently discovered Tucana 2, stretch far beyond their visible boundaries in vast halos of dark matter, their outer stars orbiting so slowly they're barely bound at all. These fragile structures shouldn't have survived billions of years of galactic tides, yet here they are, defying expectations. Dwarf galaxies also hold clues to one of cosmology's biggest headaches, the missing satellites problem. Simulations predict our Milky Way should be surrounded by thousands of small dark matter clumps, yet we found only a few dozen. Are the rest too faint to see, or does dark matter behave differently than we thought? Ultra-faint dwarfs like 1, with its mere handful of stars, might hold the answer. Their very existence suggests dark matter may be warmer or more dynamic than traditional cold dark matter models assume, potentially explaining the discrepancy. And let's not forget their role as galactic building blocks. The prevailing theory of galaxy formation suggests giants like the Milky Way grew by cannibalizing countless dwarfs over billions of years. The Gaia spacecraft has already found stellar streams in our galaxy's hail, ghostly remnants of dwarfs long since torn apart, but some, like the Large Cloud, are still fighting back. Recent studies show it's dragging a wake of dark matter behind it as it orbits, distorting the Milky Way's outer halo in ways we're only beginning to map. From preserving the universe's primordial gas to challenging our understanding of dark matter, these tiny galaxies punch far above their weight. They remind us that in the cosmos, size isn't everything. Sometimes, the smallest packages contain the biggest surprises. At the heart of every galaxy lies a sleeping giant, a supermassive black hole millions to billions of times heavier than our sun. But when these cosmic monsters awaken to feast, they don't just consume quietly. They transform their entire galactic home into the beacons in the universe. Meet Quasars, the universe's ultimate powerhouses, where a single black hole's feeding frenzy can outshine every star in its host galaxy combined. The numbers defy belief. A typical quasar emits thousands of times more energy than our entire Milky Way, all from a region no larger than our solar system. This isn't just starlight. It's the glow of matter heated to millions of degrees as it spirals toward oblivion, converting mass into pure radiation with terrifying efficiency. The secret to their brilliance lies in their accretion disks, swirling maelstroms of gas and dust orbiting at nearly light speed. Friction within these disks heats the material until it glows white-hot, emitting everything from X-rays to radio waves. But the real spectacle begins when magnetic fields channel some of this infalling matter into jets, twin beams of plasma shooting outward at relativistic speeds. These jets can stretch for millions of light years, far beyond the confines of their host galaxy, etching intricate patterns across the cosmos. The Quasar 3C273 holds the record for the longest jet observed, a staggering 4.7 million light-years long, a filament of energy that could bridge the gap between our Milky Way and Andromeda 50 times over. Now imagine one of these jets aimed directly at Earth. That's a blazar, a quasar's high-energy cousin whose relativistic beam points right at us like a cosmic lighthouse. 421, one of the closest blazars, offers astronomers a front-row seat to extreme physics. Its brightness fluctuates wildly, sometimes doubling in intensity over mere hours, revealing details about the black hole's spin and the jet's structure. These variations happen because the jet isn't a smooth flow but a turbulent cascade of shocks and knots, each amplifying the light we observe. What makes blazars particularly valuable is their ability to accelerate particles to energies far beyond anything we can achieve in laboratories. Some emit gamma rays so powerful they could, if not for our atmosphere's protection, deliver a lethal dose of radiation from billions of light-years away. These photons carry clues about the jet's magnetic fields and the black hole's rotation, hinting at how spacetime itself twists near the event horizon. Yet quasars and blazars aren't just cosmic curiosities, they're time machines. Because light takes billions of years to reach us from the most distant examples, we're seeing them as they were when the universe was young. Their prevalence in the early cosmos suggests supermassive black holes grew astonishingly fast, challenging our models of galaxy formation. Some theories propose they sprouted from massive primordial gas clouds collapsing directly into black holes, skipping the star stage entirely. Others suggest they grew via relentless mergers in densely packed galactic environments. The story doesn't end with their brilliance. Quasars eventually run out of fuel, their furious glow dimming to a faint whisper. But in their prime, they shape the universe around them, their radiation ionizing intergalactic gas, their jets carving cavities in galaxy clusters, and their energy influencing star formation rates across entire cosmic epochs. Even in their quiet phases, the black holes they leave behind continue to govern their galaxy's fates, proving that the most luminous beasts in the cosmos are also its most enduring architects. Galactic winds are the universe's great recyclers, powerful currents of gas and energy streaming out of galaxies at millions of kilometers per hour, sculpting their futures in ways we're only beginning to understand. Picture the starburst galaxy Messier 82, a celestial fireworks display where stars are born 10 times faster than in our Milky Way. But this frenzy comes at a cost. The combined fury of supernova explosions and radiation from young, massive stars creates a hurricane of hot gas that blasts outward, carrying with it the very material needed to make more stars. It's a self-regulating cycle. The more stars form, the stronger the wind and the more gas gets expelled, eventually putting the brakes on further star birth. Without this cosmic feedback, galaxies like M82 would burn through their fuel in a cosmic blink, leaving behind nothing but dying embers. These outflows aren't just about quantity, they're about quality too. As the wind races through a galaxy, it sweeps up heavy elements forged in stellar cores and supernovae, carbon, oxygen, iron, and hurls them into intergalactic space. The stream, a ribbon of gas trailing our Milky Way's satellite galaxies, is laced with these enriched materials, evidence of ancient winds that escaped their home galaxies billions of years ago. This pollution is vital. Without it, the universe would lack the raw ingredients for rocky planets, organic molecules, and life itself. Black holes add another layer to this drama. When supermassive black holes at galactic centers awaken as quasars, their radiation and jets can drive winds far more powerful than starbursts alone. The quasar SDSS J1106+1938 boasts an outflow so intense it ejects 800 solar masses of material every year, enough to empty a galaxy of its gas in just a few million years. Yet paradoxically, these cataclysmic events might also spark rebirth. By clearing away old, dense gas, black hole winds can create conditions for fresh gas to cool and flow inward, setting the stage for a new round of star formation in the galaxy's outskirts. The balance is delicate. Too weak a wind and galaxies overheat or choke on their own exhaust. Too strong and they're left gas-starved and sterile. Computer simulations show that without these outflows, galaxies would either form all their stars at once in a catastrophic burst or sputter out prematurely, their potential locked away in hot, unmoving gas. It's a cosmic Goldilocks scenario, just enough feedback to regulate growth without stifling it entirely. Even now, the Milky Way experiences its own gentle version of this process. Faint X-ray bubbles stretching above and below our galactic plane reveal traces of past outflow activity, likely triggered by our central black hole's long-ago feasts. Meanwhile, distant galaxies observed by telescopes like ALMA show winds so massive they're visible across billions of light years, their signatures etched into the subtle shifts of atomic and molecular lines. These observations are transforming our understanding of galactic ecosystems, not as isolated islands, but as dynamic participants in a vast, interconnected cycle of matter and energy. Galactic winds remind us that creation and destruction are two sides of the same cosmic coin. The same forces that strip galaxies of their star-forming fuel also seed the universe with the elements needed for new beginnings. It's a story written in the rise and fall of stellar generations, where even the most violent events serve a larger purpose, keeping the great galactic story alive, one outflow at a time. Galaxies don't always collide head-on. Sometimes they steal from one another in a slow-motion heist, leaving behind glittering trails of stars like cosmic fingerprints. These tidal tails, stretching hundreds of thousands of light years across the void, are more than just debris. They're the universe's way of keeping receipts. The stream, a shimmering ribbon of gas and stars arcing behind the large and small clouds, tells a particularly vivid story. Once thought to be torn from these dwarf galaxies as they orbited the Milky Way, newer simulations reveal a twist. It's actually the Milky Way's own gravity that's stripping material from its smaller neighbors, stretching their gas into a luminous trail that wraps nearly halfway around our sky. But tidal tails aren't just passive remnants, they're celestial detective tools. By mapping the motion of stars within them, astronomers can reconstruct ancient collisions like forensic scientists piecing together a crime scene. Take NGC 4062, a galaxy with twin tails flaring outward like comet streaks. The stars in one tail move toward us, while those in the other recede, proof that this galaxy recently swallowed a smaller companion, their mutual gravity flinging stars into opposing streams during the chaotic merger. These patterns are cosmic clocks, letting us date the collision to within a few 100 million years, a blink in galactic time. The real revelation, though, is how tidal tails expose dark matter's hidden hand. When galaxies interact, their visible stars and gas are just the tip of the iceberg. It's their dark matter halos that dictate how the debris scatters. The Sagittarius dwarf spheroidal, a satellite galaxy being cannibalized by the Milky Way, has left behind not just one but multiple stellar streams orbiting at different angles. This intricate web of debris betrays the shape of our galaxy's dark matter halo, revealing it isn't perfectly spherical but slightly flattened, like a squashed beach ball. Without these tracers, we'd have no way to map the invisible scaffolding that makes up 85% of our galaxy's mass. Some tales even defy expectations. The Antlia II dwarf galaxy, discovered in 2018, sports a tidal stream far more massive than the galaxy itself, a ghostly echo of a much larger structure that's been almost entirely dismantled. Others, like the Orphan Stream, weave through the Milky Way's halo with no obvious parent galaxy at all, suggesting they're the last remnants of systems torn apart so completely that only their debris remains. These orphan stars are like pages ripped from a galactic history book, their chemical compositions hinting at origins in long-vanished dwarf galaxies. What's astonishing is how long these structures persist. The stars in tidal tails don't just disperse, they follow precise orbits dictated by their host galaxy's gravity, forming coherent streams that can last for billions of years. The GD1 stream, for example, is so pristine it must have formed in near isolation, undisturbed by passing gas clouds or other galaxies. Its stars move in lockstep, a stellar parade frozen in time, while newer streams like Jalum show kinks and gaps, evidence of close encounters with dark matter clumps too small to see directly. As telescopes like Observatory come online, they'll uncover thousands more of these stellar rivers, each a thread in the grand tapestry of galactic evolution. Already, projects like the Dark Energy Survey have mapped dozens, revealing patterns that challenge our models of how galaxies grow. Some streams are too wide, others too curved, their shapes whispering of dark matter's quirks or unseen galactic encounters. They remind us that galaxies aren't static islands, they're dynamic beings, constantly reshaping themselves and their surroundings, leaving behind trails of starlight as breadcrumbs for us to follow. Ring galaxies are the universe's most striking cosmic accidents, flawless circles of starlight where chaos and symmetry collide in perfect balance. This object, the archetype of this rare breed, floats 300 million light-years away like a celestial bull's, its golden core encased by a shimmering blue ring of newborn stars. This isn't some delicate arrangement held together by gravity's gentle touch. It's the aftermath of a high-speed galactic hit-and-run, frozen in time. The secret to these perfect rings lies in a cosmic game of gravitational pinball. When a smaller galaxy plunges straight through the heart of a larger spiral, the collision sends shockwaves rippling outward like stones dropped in a pond. These waves compress the victim galaxy's gas, triggering a firestorm of star formation at the precise point where the pass is. The result: a dazzling ring of young, blue stars blooming outward while the original galactic core, undisturbed at the center, continues its quiet existence. It's as if the universe took a snapshot of the exact moment of impact, then hit pause on the aftermath. What makes objects so mesmerizing is its eerie symmetry. Unlike messy merger remnants, its ring forms a near-perfect circle, suggesting the intruder galaxy struck at a near-perpendicular angle. Computer simulations reveal these bullseye patterns only emerge under precise conditions. The intruder must be small enough not to fully disrupt the larger galaxy, yet massive enough to send a clean density wave through its disk. The rarity of these alignments explains why fewer than 1 in 10,000 galaxies sport such pristine rings. But rings aren't forever. Over hundreds of millions of years, the newborn stars in the ring will drift outward, their orbits perturbed by passing galaxies and internal dynamics. The ring itself may sprout spokes or fragment into arcing streams, as seen in the Cartwheel Galaxy, another ring structure with a more complex wagon wheel appearance. These imperfections are cosmic clocks, telling us how long ago the collision occurred. This object's flawless form suggests its collision was relatively recent, while the frayed edges of galaxies like AM064474 reveal older, more disturbed histories. The real surprise, some rings aren't products of collisions at all. A handful of galaxies like NGC 6028 form rings through internal processes, bars of stars funneling gas toward the center until it ignites in a circular starburst. Others may be optical illusions, the result of fortuitous alignments between distant galaxies and foreground objects. Yet none match the perfect storm of violence and beauty seen in true ring galaxies, where destruction and creation dance in luminous harmony. These cosmic bullseyes remind us that galaxies aren't static paintings but dynamic systems, their forms constantly reshaped by encounters both brutal and delicate. Each ring is a temporary masterpiece, a fleeting alignment of time, gravity, and chance that will one day dissolve back into the chaos from which it came, leaving only starlight as evidence of its brief, perfect symmetry. Dragonfly 44 shouldn't exist. This faint smudge of a galaxy, lurking in the Coma cluster, emits barely 1% of the Milky Way's light, yet the motions of its stars reveal a shocking truth. Beneath its unassuming glow lies a dark matter halo, so massive it defies every expectation. For every visible atom in this cosmic ghost, there are 10,000 particles of invisible matter, a ratio that turns galaxy formation theories upside down. How did such a dark matter-dominated anomaly emerge? And what does its existence mean for the story we've written about galactic evolution? The mystery begins with the stars themselves. Unlike typical galaxies where stellar populations trace graceful spirals or smooth ellipses, Dragonfly 44's stars drift like lonely ships in an endless sea. Their sparse distribution suggests they formed under extraordinary circumstances, perhaps in a fleeting burst of star birth that flickered out before most of the gas could ignite. One theory points to an ancient cosmic quirk, a pocket of pristine gas so devoid of heavy elements that star formation sputtered instead of exploding. Without the chemical catalysts forged in supernovae, gas clouds in Dragonfly 44 may have collapsed inefficiently, leaving behind a skeleton of dark matter and a scattering of stars too few to light the void. But dark matter's role here is even more perplexing. In most galaxies, dark matter's gravitational pull balances the kinetic energy of stars and gas, creating stable orbits. Dragonfly 44's dark matter halo, however, is so disproportionately massive that it should have attracted far more gas over billions of years, enough to birth new stars and erase its ghostly appearance. The fact that it didn't implies something intervened. Perhaps violent encounters with neighboring galaxies stripped away its gas reserves early on, or maybe its dark matter behaves differently than predicted, resisting the collapse of ordinary matter in ways we don't yet understand. The plot thickens when we compare Dragonfly 44 to other dark matter oddballs. Ultra-diffuse galaxies like NGC 1052, which astonishingly lacks dark matter entirely, present the opposite puzzle. If dark matter is the universe's galactic glue, how did this galaxy form without it? Together, these outliers bookend a radical idea. galaxies might not need a one-size-fits-all recipe. Some could assemble around dark matter anchors, while others, through chaotic interactions or rare environmental conditions, might bypass it entirely. This isn't just academic curiosity. Ghost galaxies like Dragonfly 44 are cosmic laboratories, their extreme properties magnifying subtle physics that's invisible in normal galaxies. Their dark matter halos could reveal whether this mysterious substance interacts with itself, creating friction that alters galaxy evolution. Or they might hint at dark matter's temperature, whether it's cold and slow-moving, as most models assume, or warm, with particles fast enough to resist clumping tightly around small galaxies. The stakes are high. If our theories can't explain these shadows in the cosmic web, we might be missing a fundamental chapter in the story of structure formation. Dragonfly 44 and its kin force us to confront an unsettling possibility: that dark matter is stranger and galaxies more diverse than we ever imagined. As telescopes like Observatory scan the skies for more of these phantoms, each discovery peels back another layer of the universe's best-kept secrets, one ghostly galaxy at a time. Galaxies breathe not in gasps of air, but in great cosmic rhythms where waves of star formation rise and fall like seasons on a world without end. The Triangulum Galaxy, M33, is a perfect example of this celestial pulse. Unlike the Milky Way's steady star-making pace, M33 experiences bursts of stellar birth separated by quieter lulls, its spiral arms flaring with blue clusters before dimming again. This isn't random chaos. It's a delicate balancing act between gravity, gas, and the galaxy's own structure, a cycle that turns galaxies into living, evolving entities rather than static islands of stars. The engine behind these galactic seasons lies in the interplay between gas supply and consumption. Imagine a reservoir feeding a hydroelectric dam. When water flows freely, power generation surges, but as levels drop, output dwindles until rains replenish the source. Galaxies operate similarly. Cold gas, the raw material for stars, pools in their spiral arms until gravity triggers collapse, igniting stellar nurseries. But this frenzy doesn't last forever. Massive stars born in these bursts die quickly as supernovae, their explosions heating surrounding gas and blasting it away like a cosmic wind, temporarily stifling further star formation. The galaxy must then wait for fresh gas inflows, either from intergalactic filaments or mergers with smaller companions, to refuel the cycle. External forces add another layer to this rhythm. M33's interactions with its colossal neighbor, the Andromeda Galaxy, periodically tug at its gas reservoirs, compressing clouds and sparking new rounds of star birth. Even passing through denser regions of intergalactic space can trigger these episodes, as ram pressure strips away loose gas while simultaneously squeezing what remains. It's a galactic seesaw, disruption and replenishment, boom and quiet, all woven into the fabric of cosmic time. The aftereffects linger like footprints in snow. Each starburst leaves behind chemical signatures. Heavier elements forged in stellar cores enrich the remaining gas, making future generations of stars slightly more metal-rich. Over billions of years, these cycles subtly alter a galaxy's composition, its very color shifting from the blue of hot young stars to the redder hues of aging populations. Yet some galaxies, like M33, resist this aging process longer than others. Their ability to tap into fresh gas supplies, whether stolen from neighbors or drawn from the cosmic web, keeps their star-forming seasons robust, stretching their prime far beyond what their size alone might predict. What's most astonishing is how these cycles echo across scales. The same gravitational collapses that create stellar nurseries within galaxies also govern the ebb and flow of star formation in dwarf galaxies and even the vast, star-forming regions of galactic clusters. It's a universal cadence, a slow cosmic heartbeat written in the rise and fall of starlight. And just as Earth's seasons shape ecosystems, these galactic rhythms dictate where and when planets might form, where life's building blocks could emerge, and ultimately, how galaxies write their legacies across the deep time of the universe. The universe's final act isn't a dramatic explosion or a fiery collapse. It's a slow, quiet fading, like embers cooling in an endless cosmic hearth. Picture a time trillions of years from now, when the last stars have burned out, black holes have evaporated, and galaxies exist only as faint ghosts of their former selves. Space itself has stretched so thin that even the memory of light becomes diluted, leaving behind a vast, near-empty expanse where temperatures hover just fractions of a degree above absolute zero. This is the heat-death scenario, a future where entropy wins and the universe reaches maximum disorder, its energy too diffused to power even the simplest processes. But what if death isn't the end? Some theories suggest the cosmos might have a trick up its sleeve. Conformal cyclic cosmology, proposed by physicist Roger, offers a breathtaking alternative. The universe could be cyclical, with each ending in a state mathematically identical to the conditions at the Big Bang. In this model, when all matter eventually decays into radiation and particles lose their mass, the universe becomes smooth and featureless. But this very emptiness mirrors the primordial singularity from which our own cosmos sprang. The end becomes a new beginning, with gravitational waves from ancient black hole mergers imprinting faint patterns onto the next cosmic microwave background, like cosmic DNA passed between generations. The implications are staggering. If is right, the galaxies we see today, their spirals, collisions, and stellar nurseries, might be echoes of structures that existed in a prior universe. The same laws of physics would play out anew, forming fresh galaxies from reborn energy, their stories unfolding in ways both familiar and utterly alien. Evidence for this radical idea might already exist, and colleagues claim to have found concentric circles in the CMB, patterns they call Hawking points, theorized to be imprints of supermassive black hole collisions from a previous. Other rebirth theories take even wilder forms. The Big Bounce hypothesis suggests that if dark energy weakens over time, gravity could eventually reverse the universe's expansion, collapsing everything back into a singularity that triggers another Big Bang. String theory's landscape of possible vacuum states hints at a multiverse where new universes bud off from dying ones, each with different physical constants. And quantum fluctuation models propose that even in a seemingly dead universe, random energy shifts could spawn new inflationary bubbles, pocket universes where galaxies might rise again. Yet these visions of rebirth don't erase the profound melancholy of the heat-death scenario. Whether the universe ends in ice or fire, the galaxies we know, their stars, planets, and potential for life, are transient wonders on cosmic timescales. The Milky Way's merger with Andromeda, the blazing quasars of the early universe, the delicate dance of dwarf galaxies, all will be forgotten in a future where time loses meaning. But there's a strange comfort in this. Just as stardust recycled from dead stars built our solar system, the atoms of our galaxy might one day fuel new cosmic dawns, whether in this universe or another. The story of Galaxies, then, isn't a linear tale with a final period, but an ellipsis, an eternal question mark hanging in the dark. From their fiery births in primordial gas clouds to their quiet fade into cosmic twilight, galaxies live lives of staggering drama, each one a novel written in starlight, its chapters spanning billions of years. These 24 chronicles we've explored aren't just celestial history, they're a mirror reflecting the universe's boundless creativity. Think of the whirlpool galaxy's perfect spiral arms, where new stars ignite like fireflies along gravitational waves, or the Sombrero Galaxy's dark dust lanes, woven like ribbons around a glowing core. Every structure, every collision, every burst of star formation is a testament to nature's ability to sculpt chaos into breathtaking order. Yet for all their grandeur, galaxies are deeply personal. The iron in your blood, the calcium in your bones, these elements were forged in the hearts of stars that lived and died long before our solar system formed. When you gaze at the Andromeda galaxy, you're not just seeing a distant spiral, you're looking at a relative, a sibling in the local group whose fate is entwined with our Milky Way. The carbon in your DNA, the oxygen in your lungs, these are galactic souvenirs, gifts from generations of stellar explosions that enriched the cosmos with the ingredients for life. What's astonishing is how much we've pieced together in just a blink of cosmic time. A century ago, we debated whether galaxies were mere island universes or part of our Milky Way. Today, we map their life cycles with telescopes that act as time machines, capturing light from epochs when the universe was young. The James Space Telescope's images of infant galaxies, the Gaia spacecraft's star maps tracing our galaxy's violent mergers. These aren't just scientific achievements, they're chapters in humanity's own story of curiosity and wonder. The greatest revelation might be how unfinished this story remains. Dark matter's true nature, the mystery of dark energy, the ultimate fate of black holes, these puzzles remind us that galaxies still guard their deepest secrets. Perhaps you'll be part of unraveling them. The next great galactic discovery could come from a researcher analyzing data, an amateur astronomer spotting a supernova, or even a viewer like you gazing up at the night sky with fresh questions. So tell us, which galactic chronicle captivated you most? Was it the violent beauty of colliding spirals, the eerie glow of quasars, or the quiet resilience of dwarf galaxies clinging to their dark matter? Drop your thoughts below, and if you've enjoyed this journey through the life cycle of galaxies, hit subscribe to explore more of the universe's grandest tales. Wherever you are, whatever time it is, remember, you're standing on a planet orbiting one star among hundreds of billions, in a galaxy that's just one voice in a cosmic chorus. The night sky isn't just above us, it's within us. Keep looking up and let the stars remind you how extraordinary it is to be part of this story.